Okay, in this flipped classroom video, we are going to investigate characteristic functions called inverse functions. It's not like polynomial functions or rational functions, like it's a type of functions. I guess it probably could be better said if we said what we're really studying are the inverses of functions. Inverses, it's a relationship between two functions. It's something that we do to one function and create a new function. So we kind of shorthanded to inverse functions, but it's probably better said the inverses of functions. This is something that we're going to use for a lot for the rest of the year in our study of between exponential and logarithmic functions, and especially as we go through trigonometric functions between now and the rest of the course. If we want to start with a very basic sort of easy definition, this is definitely an informal definition. It's about two functions that undo each other. What we would have, if I started with the function f of x equals 2x plus 6, if I wanted to find, let's say, if I used an input of, let's say, 4, and I put a 4 into the first function, well, 4 times 2 is 8, and 8 plus 6 is 14. So I have an input of 4, I have an output of 14. Well, what an inverse function would do, an inverse function would take that 14, drop it into the inverse function. It undoes what the first function did and gives me my 4 back. Excuse me. And this inverse, and I don't know what the rule for this inverse is yet. We don't need to know what it is yet. Eventually we'll find those. But that's the idea of what an inverse function does. It undoes. If you want to think of one function as a factory or a machine that puts something together and builds it, the inverse function takes it apart. And I could do this for every possible input into the function f. I could change my input, and I could use an input of -7. If I take -7, put into the function, 2 times -7 is -14. -14 plus 6 is going to give me -8. And then that inverse of f, whatever it happens to be, is going to take that -8, undo what f did to get it, and I'm going to get my -7 back. And that's what an inverse function does. Now, if I generalize this and I say, well, we're talking inputs and outputs and we're using numbers here, more generally what happens is I put in some x, I get out some y from a function. I would take that y, put it into the inverse, and I would get my x back. And that's the undoing there. If I look at this, this kind of looks like our composition of functions. And since I'm going to say it works for all of the functions, I can generalize even more. And instead of using a specific 1x and 1y and getting the x back over there, I could use the collection of all of the x's, which means if I put in the domain of f, that's all of the x's put together, I get out the range of f, you know, all the collection of all the different outputs of f is called the range of f. I take those range values of f, put them into the inverse function, and I get my original values back, so I'm getting my domain of f back over here. And what is very interesting here is that this range of f also acts as the domain of f inverse. So those numbers in the middle there that are in the yellow box, those numbers that come out of f, therefore they're the range of f, are the numbers that go into f inverse, therefore they are the inputs into f inverse. They have this dual role that they are both at the same time, and maybe I should make this a double arrow, that those two sets are the same sets of numbers. The range of f and the domain of f inverse are the same sets of numbers. Just like over here, if I take this set of numbers right here, they are simultaneously the domain of f, but since they are also the numbers that are the outputs of f inverse, they are the range of f inverse. And that's a very important statement there. And maybe we'll summarize that on the next slide here. If a function's domain is a set of numbers D, and its range is a set of numbers R, then that function's inverse has a domain of R and a range of D. Now remember here, I'm using capital letters for D and R. So they're not numbers, they're not variables, they're sets. They're representing the set of all of the x's and the set of all of the y's. So it's a little strange to be putting an R as a domain. But we can see here that for our original function has a range of R. Now if I go back to my slide and I look here, the original function's range is also the inverse's domain. So if I call this, and I choose a different color here, if I call this capital R, then this is also capital R. Saying that the range of f, I can move that R out of the way, the range of f, call that R, is the same as the domain of f inverse, call that R as well. And that's what I'm saying here. And vice versa with the domain of the function being D, then the inverse has a range of D. So that's a very, very important relationship. And let's illustrate it with an example of a function that we know quite well here. We have f of x equals x squared. And for this f of x equals x squared, if I choose some points on it, for example, if I choose the point 0, 0, that means I'm inputting a 0, outputting a 0. We would have the point 1, comma 1. I'm inputting 1, I'm outputting 1. 2, comma 4, you know, and so on, and 3, comma 9. But also I'd have the negatives as well. I would have negative 1, 1, negative 2, 4, and negative 3, 9. Now, the inverse, the potential inverse, if I take my previous statement, what that means is my output values of the function are the input values in the potential inverse. And the input values that were in the function will be the outputs of the inverse. And that's what was illustrated in this picture. So that means if the function has the point 0, 0, I switch them, the potential inverse has the point 0, 0. If the function has the point 1, 1, and I reverse them, I have 1, 1. Then that's kind of, it's a little weird because they have the same value, so it's not illustrated very well. But when I get to the point 2, 4, if I put 2 into the original function and I get out a 4, that means the 4 would be the input into the inverse, and the 2 would be the output. And the same with 9, 3, but also the same with the negatives. I'd have 1, negative 1, 4, negative 2, and 9, negative 3. Now, if I take those points for those inverse and I plot them, I could have 0, 0, 1, 1, 4, 2, 9, 3, but also 1, negative 1, 4, negative 2, and 9, negative 3. And this is the graph that I would get. And there's a couple of things that I should notice here about what's going on. And the first and most important is to say that the potential inverse here fails the vertical line test. If I were to take a vertical line and scroll it across the coordinate plane, well, clearly this inverse fails the vertical line test. And so what we would say is that the function f of x, the function f of x equals x squared, does not have an inverse function. because the inverse has to be a function. We are restricting ourselves to functions. So while f of x is a function, its potential inverse fails the vertical line test. It's not, that inverse would not be a function. So we say f of x equals x squared does not have an inverse. More properly, we say f of x equals x squared does not have an inverse function. Very often we do not say that word there, and we just say inverse, and that word function is kind of implied there. All right? So that's the kind of the big idea about what inverses are. And in class, we're going to talk more about which functions do have inverses, which ones don't have inverses, the relationship between a function and its inverse, and the graphs, and all that sort of stuff. We're going to get into the nitty-gritty. But this was just to get you started, so we come into class, we've got a good jump on some of the material there.